What's going on, folks? Can you hear my voice? Can you see my face? Can you hear everything? Should we get started or should we wait the 2 minutes? What are your thoughts? What are your thoughts? I still sound sick. I kind of am. I'm still getting over it, man. It's like, it's nuts. Anyway, I'll tell you what. You know this really big assignment? I'm feeling like, what are your thoughts on this thing? Is it like getting really out of hand, like it's super huge? Or Or is this like, is it not so bad? Have you guys started working on it? Because to be honest with you, like I sat down with Raven yesterday, and we basically she sat down. She got some tutoring from me, and we both sat down and did the problem or the homework or this thing, and we got through like half of it in a couple of hours, and it wasn't so bad. Like it's not as bad as you guys might think it is, because a lot of it was really just review. You know, like it's remembering. Oh, wait a second, that's how this thing works. You know what I mean? It's not hard. It is long, but I did give you a week and a half with no other assignments. It's hard to remember everything, but I'm totally allowing you to look it up, and that's kind of the point. Um, I'd rather you have trouble remembering it now, and then have taken the time to look it up, than um, I'd rather you have trouble looking it up now and figuring it out than going to the test and being like, oh, that's hard to remember. You know what I mean? That would suck a lot more than anything than like trying to figure it out now. Is when you're on the test and just like, oh, I remember seeing this, but I don't remember this at all. So I'd rather you struggle with it now than struggle with it next in 2 weeks from now. Because I want you to pass this test. I want you to do well on this test, and that's really more of a it reflects good on you part. So we talked about S waves and P waves, and what I plan on doing is hopefully I'll get through a good chunk of this class, and then next week I'll have it set up so that we'll basically do the same kind of questions. Just this time we're going to do like more of a Jeopardy style and that kind of thing. But for today's class, what I plan on teaching you guys is re-teaching you the rest of this assignment. So it's in essence, I'm actually, you guys are saying it's hard to remember this stuff, but I spent the whole class last time talking about S waves and P waves and the mechanical waves and dampening and that kind of stuff. So we got through a good chunk of this thing, and then today I'm going to today what I'm going to do is I'm going to go over the rest of the assignment with you. So in essence, even though this is a long assignment, I'm pretty much going over a good chunk of it with you in class. You know what I mean? So that's pretty nice. That's pretty cool, Mr. Dalday. So it's not even going to be really that bad, I feel like. Let's see. What is something else? Oh yeah. Sophia is saying you're using your old assignments as references, and in fact, actually, what I did was I actually took a lot of this, a lot of these questions and took them out straight from your old assignments. So even like the Crayon Rock Lab, obviously you don't have to do the Crayon Rock Lab. If you already did it, I'm not expecting you to redo it. I don't really care about you redoing it. But what I'm asking you to do is I'm asking you to just kind of like remember what those rocks kind of did. You know what I mean? Like remember what you did and tell me what you did. So don't redo the lab. I mean, if you did it once, then you did it already. I don't really care about you redoing it. I'm not going to expect you to remelt crayons or that kind of stuff. But what I'm asking you to do is kind of just remember this stuff. We cool? All right, so let's talk about gravity. We're talking about the gravity, I'm introducing to you an equation. It's called the universal gravitational, or the universal equation of gravity, and I'll show it to you what it looks like, and I'll show it to you right now. It goes like this. What if we did force? Write this down if you need to.
Sorry, my computer's not responding. Give me a second. It will come up. Force of grav is equal to G m1 m2 over r squared. I don't expect you to remember this. Yes, I am recording. I think I am at least. I don't expect you to memorize this equation. I don't expect you to really know how to use this equation, but I expect you to be familiar with this equation. I'm going to introduce it to you. All right? It's force is equal to big G m1 m2 over r squared. The big G is called the universal
gravitational
constant. It's a number. That's all it is. Nothing but a number. That's all it is.
It ain't nothing but a number. It's like the number pi, but it's a different number than pi. It's just a number. Okay,
so don't worry really about what that is. Just know that that's some number that you would need. We call that a constant, actually. Well, hence the name constant.
All right, M1
and M2, that stands for the mass of the objects.
Are we cool? And then the R
stands for the distance
in between. Yes, I put R. Sometimes you see it as D squared, but I mean, it really doesn't matter. I mean, it's the same thing. You're talking about the distance in between, and I call it R because usually when we're talking about like gravity, we're talking about
gravity between planets, and when we're talking about planets, we're talking about big circles like this. And so it would make sense for me to call it R because that's the radius or something like that.
Are we cool? Does that make sense to you? But in essence, I don't necessarily, you know my pet peeve. I hate pulling equations out of my butt and throwing it up on the board and saying, memorizing this. And I didn't pull it out of my butt, but I mean, I pulled this out of thin air and I told you, hey, look at this equation, remember it. Don't memorize it, but just be familiar with it. So what I want to try to do is I want to try to kind of justify what's going on. Sound good? All right. So all this thing is saying is this. In fact, this is what I have you doing. Open up this tab right here, and it's pretty straightforward. Actually, you know what? Let's read the instructions, and we'll do it together. All right. How does the gravitational force of a small mass has towards the large mass compared to the what physics law could you read? All right. Design a experimental relationship to the mass. Or find the best equation for the mass. All right, cool. All right. So check this out. I've got two people, and they are holding planets, and they're small planets. They're like planets that only weigh a kilogram and a kilogram. Got it? Now the force in between these two objects is going to be really small because we're talking about 1 kilogram and 1 kilogram. It's not like those things attract each other, you know what I mean? But what force is this object right here? What force is this guy going to feel? Well, okay, fine. Something like 0.00000040 newtons. Got it? And what force is the red guy going to feel? He's going to feel 0.000040 newtons. So apparently, this blue object is attracted to the red object as much as the red object is attracted to the blue object. Does that make sense to you? They're attracted the same amount. In essence, the Earth is pulling you down, right? The Earth is pulling you down because you have a mass and the Earth has a mass, and the Earth is super massive, it's super big. It's pulling you down with a certain mass, or a certain force. We call that force our weight, right? But could I ask you this? Are you pulling up on the Earth, with that same force? If the Earth is pulling me down with a force of
150 pounds, does that mean I'm pulling up on the Earth with a force of 150
pounds?
And the answer is yes.
I'm pulling
all forces. There exists an equal and opposite force. That's Newton's laws. So the equal opposite force, if Earth is pulling me down at 150 pounds,
technically I'm pulling the Earth up at 150 pounds.
Does that make sense?
So everyone technically is
pulling up on the Earth with whatever force that the gravity is pulling down on them with. It's equal and opposite. Now, if I jump out the window over here, because I'm on the second floor, if I jump out the window, I'm going to fall down. You guys agree?
But does that mean that
the Earth is going to kind of
move up? Why do I move down and the Earth doesn't move up? Exactly, Raven. It's really because the Earth does move up. It just moves up a lot less than I do. I'm way less massive than the entire Earth is. So even though the forces that are pulling us are the same, it'd be like saying, all right,
fine, do this. Take 150 pounds and push with that force of 150 pounds.
Push a red wagon. Is the red wagon going to go far? Yeah, sure. You push with a force of 150 pounds, you push a little red wagon,
it's going to go far.
But now, why don't you push with 150 pounds, push a battleship? Like an aircraft carrier. How's that? Push an aircraft carrier. Aircraft carriers are like the size of a couple football fields. So you go over to the docks and you're pushing with 150 pounds. Is that thing going to move very far? Right. You're going to barely move it at all.
And that's what I'm saying. I mean, imagine how much bigger the Earth is than a battleship.
It barely moves. So I can't say that
the Earth doesn't move, but it just doesn't really even feel you.
You know what I mean? It's like, whatever. All right. Now here's something interesting. All right, cool. Let's check this out. You ready? If I make the mass, so right now I have a mass of 1 kilogram and I have a mass of 1 kilogram. And notice the force. Let's say that the force, let's get rid of all those zeros in front. Let's say the force is 40 newtons in between both of them. Are we cool? All right. Now what I'm going to do is I'm going to go like this. I'm going to change the mass of the second one, so that red one. See how that red one's a little bit bigger than the blue one? I'm going to change that mass to be twice as big.
Got it?
What happened to the force? I'm going to change the mass to be twice as big. What happened to the force? It doubled. All right, so if I double the mass, I'll double the force. You guys see this? So if I double the mass, I double the force. And if I look back at my thing right here, if I replace m2 with 2m, all right, so I have, what's my new force of gravity? It's gm2m over r squared. So I kept the r the same, I kept the first mass the same, but this one is 2 times the mass. Then essentially it would just be twice gmm over r squared, or my force would be twice the force that I have. Are we cool? So changing the mass, I mean, if I'm talking about a more massive object, then your force is going to get bigger. All right, let's bring that back down. Okay, So if I double the mass, I double the force. All right. What is another way that I can change the force in between these two things? The distance. Very good. Exactly. The distance. If I put them further away, what would happen to this force? Would it go down or up? All right. So if you make the distance bigger, the force will actually go smaller. They're inverted, right? If I make the distance big, the force would go small. And if I make the distance small, the force would go big, right? So that's why the distance is in the denominator. That's what the denominator does. If a denominator becomes big, then the overall number becomes really small. That's why that radius is in the denominator. Do you understand? Like, oh, I get it. He's explaining why the equation looks the way it looks. Are we cool? All right, so what's going on is, let me ask you this. If I doubled the mass, remember when I doubled the mass, I made this thing twice as big? It doubled the force. What if I double the distance? What if I make the distance twice as much? What would happen to the force? So right now, how far apart are they? They're about 1 meter. Okay? It's about 1 meter. A little bit bigger. If I move this guy to 2 meters, how would this change? Victoria is saying it would only be 2 times smaller. Raven is saying it would be 4 times smaller. Lucas is saying it would be 4 times smaller. Nicholas is saying it'd just be smaller. Okay, I agree with Nicholas that it would be smaller. I like the detail that they would give, that people are giving, though. Where are you getting the number 4? Where are you getting those numbers? All right, here, why don't we test it out? Why don't we try it out? Let's see. I'm going to take this guy, I'm going to move him back. Right about there. So he went from 40 to about 10. Let's round it off. 10. What happened? Why is he 4 times as small, even though I only moved him twice as far? Why did the force go down 4 times as much, even though I only moved him twice as far? Alright, so radius is in the denominator, I agree, but why did it go, why is it quartered? Ah, Raven's got it. It's because, look at this. If I put in a 2 over here, that would be, I'm going to replace an r with 2r, okay? And I square that. Then when 2r squared is actually the same as 4r squared. You guys get it? Two r squared, I got to square, 2r squared is this, 2r times 2r. 2r times 2r is 4r squared. Because the 2 times 2 is 4, and the r times r is r squared. So really what happened is, when you doubled the distance, it actually brought down that force by 4 times as much. You see what I mean? So really what we do in science is when we made up this equation, we didn't just kind of like make it up. We kind of experimented with it. We said, all right, what if I change the mass? Oh, okay, those must be in the numerator. What if I change the distance? Hey, wait a second. When I make the distance twice as much, the force went down by 4. So it must be an r squared instead of just a regular r. So changing the force makes a big difference. Are we cool? So let's see, what are the answers here? How can I do an experiment to find the best equation with mass? What I would do is I would change the mass. That's what I would do. And then what are these things? Well, I already told you all about all of them. The big G is actually called the universal gravitational constant. In fact, I actually told it to you right here. Big G is the universal gravitational constant. And then if I ask you, what happens if I increase M1? Well, the force would increase. What if I increase M2? The force would increase. What if I increase R? Then the force would do what? If I make R bigger, the force would decrease. And it would decrease
in a squared kind of way, which is really
interesting to me. You see what I mean? So look, there's your answers right there. Are we cool with that? You guys think you guys can hang with this thing? Alright. Let's take a look at this one. Do you guys feel like you understand gravity? Gravity a little bit? Where's this document? What are you talking about? Which document? The study guide? I'm pulling it straight from the study guide. I'm actually going over your homework with you. I'm assigning you this homework, but I just told you all the answers for this. So Raven's dad studies rocks, so hopefully we'll be good with this thing right here. But let's talk about this. Do you guys remember the rocks, like igneous rocks and all of that kind of stuff? Let's quickly go over the different types of rocks. Let's look at them. And all I'm going to do is I'm going to go over this website with you and say, hey, remember, all right, we got sedimentary rock. That's the one type of rock. We have, where's my rocks? All right, here's my rocks. So we have these sedimentary rocks, and those include the conglomerate, or the sandstones, or the limestone, or the shale, or the siltstone. And if you feel them, they're all real nice and soft. They're nice soft rocks. Cool? Then the next set of rocks we have is the metamorphic rocks. The metamorphic rocks include these guys down here. They include the talc and the marble and the slate. And those are pretty nice ones too. They're still a little rough, but they're they're a little harder. They don't crumble as much. And then the last one we're talking about is the one called an igneous rock. And the igneous rock, those guys over here, they include pretty much everything you find in Hawaii. Because Hawaii is the basalt, which is like right over here. Right? Are we cool with that? Alright. And then what kinds of things would you find in the different rocks? Well, you can look for crystals, you can look for fossils. By the way, if a rock has fossils inside of it, what kind of rock would that be? If a rock had fossils in it. I'm thinking sedimentary, because if it were metamorphic, then it would have had to have been like gone under a lot of heat and pressure, and that heat and pressure would have disintegrated that fossil. So it's got to be sedimentary. It's got to be just kind of like this mixture of a bunch of different junk altogether. What about a rock that has a lot of gas bubbles on it? What do you think? It's probably an igneous rock. Because, I mean, you think about it, you guys have you ever, if you've been to the Big Island, you know that when you step on the lava rocks, they have a lot of gas bubbles. And those have a lot of, and the reason why they would have a lot of gas bubbles is because when the rock forms, it's basically forms from molten lava into a rock, and then there's a lot of gas that comes out of it. You also have nice glassy smooth surfaces, and those tend to also be igneous rock as well, right? What if it has like ribbon-like layers? Like there's these nice ribbons that go across. Like, for example, this one kind of has a little bit of ribbons. You can kind of see it over here. See the ribbons that go across? It's metamorphic. What makes you think it's metamorphic? Because what it is it's kind of like a bunch of
different rocks that got pressed together. And then that pressing together kind of made it into this like this ribbon kind of thing. And that would be a metamorphic rock. And then what if it's a rock that has a lot of different kind of like junk inside of it, like sand, pebbles, that kind of stuff. What kind of rock is that?
It's a sedimentary rock, and that's
What
what
a sedimentary rock is. It's just a bunch of like stuff pushed together.
All right, so let's talk about the process of the rocks. And then after that, I only have time to probably cover the wind cycle with you, which I didn't really cover in too heavy detail. I'm going to go through quickly with this stuff, but I want you guys to, like, if you don't remember it, then read this webpage, because it will probably help you answer all the questions. You'll be fine. All right. Heat and pressure is the process of, like, an igneous rock can turn into a metamorphic rock by basically applying when it goes down into the earth and it gets pushed down into the earth, there's a lot of heat down there and there's a lot of pressure that happens over there. It's like it's pushing together. It'd be like taking your crayons and then like basically pushing them together and putting them in the microwave for a little bit. Got it? You want me to paste this thing into the chat? Alright, fine, I will. There we go. You can have a rock that melts, and then that's not a rock basically getting under a lot of heat and pressure. That's basically a rock getting super hot, and that metamorphic rock will turn into magma. Magma. And that magma is what kind of we use to make igneous rocks later on, but basically it's melted rock. We cool? We can also have cooling, and that's a different type of way a rock changes, and that's when we have melted rock comes outside of the volcano and it cools down. Why does it cool down? Because it's hitting the cold air, or at least a lot colder than where it was hanging out before, and so that's when you have this melted rock turning into what we call igneous rock. Are we good? Now, by the way, why did I call this one an extrusive? Alright, well, hey, this is a nice little thing. Alright, we can have magma that cools slowly inside of the earth, and that's called an intrusive igneous rock. Whereas we can have our lava that goes outside of the volcano, and that's called an extrusive igneous rock. And you guys are complaining, wow, that's so long ago. What do you mean, what was so long ago? Like when we covered this? Oh, Mount St. Helens. Yeah, it was. It was a long time ago. Alright. Another way a rock can change is it can weather and erode. And we talked about how it weathers. We talked about how the rain will hit it and the wind will hit it. And then remember what is it called? Ice wedging? Where the ice will go into the cracks and then freeze and open up the cracks more, and then the water will go more into the crack and then freeze and then open up the cracks more. And eventually, it will break the rock in half. Like break the half with the power of water style. That's pretty cool. Anyway, yeah, weathering and erosion will break a rock into small pieces. And we call those small pieces sediment. Do you guys remember that? It's like breaking these rocks into small pebbles. That's called sediment. The pebbles are called sediment. And there's this process called compacting and cementing, and it's basically where you take a bunch of the junk, like all the sand and the sediment, and you put it down into some place where it has a nice ability to be pressed together, like at the bottom of this river or the bottom of this ocean or whatever, and then that kind of pushes these rocks together because it's so much pressure. I mean, if you think about it, when you go down deep, dive down deep into the ocean, you feel the pressure in your ears. Well, imagine going way deep down, you feel a lot of pressure, and then that could turn like sand into rocks. And it won't be like super nicely melted together glued rocks. It will kind of be like, I don't know, like a sandy kind of rock. Yeah, you would go so far down that, say, your head shrinks. Well, and then it would turn like your head into a rock. You'd be dead, obviously, but whatever. We cool? So then we talked about, remember, do you guys remember this stuff where we talked about the rocks turning into each other? So we have like, if you, let's start off with an igneous rock. Got it? We got an igneous rock, which includes the basalt or granite or obsidian. What can an igneous rock do? Well, an igneous rock could undergo melting, and that turns it into magma. All right, that's cool. Turn it into magma. And then when it cools, it turns it back into an igneous rock. What else could an igneous rock do? It could break down. You could break it down into small little pieces, and that would turn it into what we call sediment. That's not a rock, that's just small pieces. Actually, I guess they would be considered small rocks. You could also put it under heat and pressure, and that would make it into metamorphic rock. Now, what does that sediment do? Well, the sediment can compact and cement and turn into a sedimentary rock. So that would include the conglomerate type of rock, or the limestone, or the sandstone, and all that kind of stuff. It feels really like crumbly if you break it apart. It's not that hard. Yeah, I know. You guys made a whole poster on this. I'm just trying to remind you about this. So you guys are like, oh, this thing is so hard. But remember, you did whole projects on this. I'm just trying to remind you. Hey, remember this stuff? All right. Now, what can happen to the sedimentary rock? Well, it could break down and turn back into sediment. In fact, it probably does that because it's not, it's not a very solid rock to begin with. But, I mean, it could break down and turn it back into sediment. Or you can apply heat and pressure and turn it into a metamorphic rock. And then what could that metamorphic rock do? Well, you can always break it down and turn it back into sediment. Okay, what to do? Or you can melt it by basically throwing it at the bottom of a volcano, and it melts and turns into magma, which is the stuff that you need to make an igneous rock, and therefore the cycle kind of continues. We good with this? Like, I went over it really quickly, but you remember this, right? This isn't like brand new stuff for you. And if it's brand new stuff, then you should have attended WebEx last quarter, because I was really funny back then. All right. Let's continue on our thing. And I don't think I covered too much about this in class, so I want to make sure that I have this. Let's talk a little bit about convection currents. Remember, there's different ways that a current can go. Say that I have a pot of water, and I'm heating it with fire. And what's going to happen inside of that pot? Well, the pot's going to heat up, okay? Say that it's a junk pot, and it's like it's a full metal pot, and I'm holding it without a glove. I'm just holding it with my hands. What's going to happen? My hand is going to burn. Because say that I heat the thing on an open flame and it's super hot and I just grab it. You know what I mean? That's pretty stupid, but I mean, what's happening is what we call conduction. Just like wires conduct electricity, metal conducts heat very well. And the way that's going to get heated up is it's going to conduct into my hand. That's how the metal will heat up to other parts of the metal. All right, what about, how did the fire make the pot hot in the first place? So that the fire is not touching the thing. Or when it's really cold and you have a fire outside, do you ever like go stand next to it and it's really hot? You're not touching the flame, obviously, so that's not conduction. Well, what's going on? That's called radiation. The fire is radiating heat. Does that make sense? All right. The last thing that's going to happen is this water inside is going to start to do something kind of interesting. When it's hot, and say it's heated up only in the middle, hot air rises, right? Hot water also rises. it will start to kind of go up.
So you have hot water going up. But when it hits this surface right here, what's it going to do? Is it going to continue to go out? Is it going to just kind of
Go straight up. Basically, you put a pot of water over there and the water just jumps out. No, it's gonna
split up like this? Are we cool?
it's gonna kind of like hit that surface and then like move apart.
And then when it's on the surface over here, that's kind of nice because this top layer of water is still touching the cold air, so it's going to cool down just a little bit. And then that's going to cause, and when you have cold water, it tends to fall. Cold water falls. If hot water rises, then cold water falls. So we have kind of this water cooling down, turning into the blue one, and it comes over here. But hey, when I hit the bottom of the pan, what happens again? Then it gets hot again.
And it goes up. And then comes down, and then goes up, and comes down. And basically you have this thing that we called, do you guys remember what this was called? Exactly, this was called a convection current. Now check this out, if I show you this video, you're going to look at this and be like, oh wow, that's pretty cool. Let's look at this real quick. Wait, this is continental drift. That's not necessarily the one I wanted. No, I don't want you to actually do the full convection currents lab. I want you to... let's see. Here, this might be the one I'm looking for. There we go. Do you see how the Earth can have these convection currents? The hot water will go up, then it gets, goes along here, and it gets cooled down, and it goes over here. Well, then when you play this animation, you see that, hey, wait a second, these tectonic plates are moving.
And why are they moving? Well, they're moving because
the convection current in the Earth, the magma, is moving around. You guys get it? And so, remember when we talked about convection, or when we talked about plates moving? Like, what's happening with these plates over here? See these two plates? These two plates on the left, what's happening with them? They're not converging, they're actually diverging. They're pulling apart. Alright, so you'll probably have new ocean floor underneath there. And then what's going to happen with these two plates over here? On the right, two on the right. Those are converging. They're crashing into each other. Now I got a question.
Are they subducting? Do you guys remember that word? It's like a subduction zone?
And the answer is no. These ones aren't subducting. Subduction zones is when like you have one plate coming into another and one plate goes down underneath the other plate. Like for example, usually when you have an ocean plate crashing into a continent, the ocean plate gets pushed down underneath. You guys remember that? But like these guys are being pushed, say that these are two continental plates being pushed together, they're crashing into each other and one's not going under the other. They're both kind of going like this. I'm not going to, they're both trying to like win. So then they crash and they go up against each other like this. Like they're kind of crashing and pushing up against each other. And that's actually how you form like these super huge mountain ranges like the Himalayas. You have two plates crashing into each other, and then they're both getting pushed up. So it's not one going on top of the other. This is the one where they're both kind of just trying to both go on top of each other. And neither one is winning. Does that make sense? And how does this stuff go? How does all of this stuff move? Well, it moves because of convection currents in the Earth. Now, what is transforming? Transforming is when they're moving, but they move like this. So it's not that they're crashing into each other. It's not that they're pulling apart from each other. It's that they're moving like this. Does that make sense? By the way, I'm showing my camera, so if you can't see my camera, then you're like, what is he talking about? They move kind of rubbing together like that. We cool? Alright, let's talk about this because I don't have a whole lot of time and I want to get through this as best as I can. I'm going to talk about the Earth. I'm going to find a picture of the globe. And remember, I didn't have this computer set up for what I wanted to do with it just yet. So let me see. Globe, Earth. Let's grab an image from there. I need an image of the globe. And we talked about convection current. We talked about conduction. So let's talk about a picture of a globe. This will, let's see where, it's a good one. I don't want a side view. Yeah, this might work. No. This won't work. No. Let's see. Globe map. There we go. This will work. Alright, fine. This will be good. Let's do this one. Copy image. And paste image. Okay, wait, my computer's not responding. I gotta get it up. Hold on. Whoa. Whoa. That's a big one. Alright. It's alright. Let's zoom out. Perfect. Alright, awesome. Alright, so check this out. Let's start talking about this thing. Can you guys see the world on the right-hand side? It's got Africa. It's got Asia in there. We're looking at that place over there. We're cool. Alright, so check this out. This is the equator right here. And if I were to actually draw a better picture of this globe, which maybe might be in order, but I would have to tilt it, wouldn't I? Like, wouldn't I have to tilt this thing 23 something degrees? 23.5 degrees even? But anyway, here we have our equator right there. And yeah, you're right, I would have to tilt it. But, well, I didn't find a tilted globe, so I've got this one right here. Now, let's say that we have the sun coming down. And the sun's coming in, and it comes in kind of basically straight like this. We good? So, what happens? Well, what's happening is the sun hits the equator nicely at almost a 90-degree angle. In fact, when we talk about this thing called an equinox, that's where we're talking about the sun hitting at almost exactly 90 degrees. In fact, on Maui, they actually have the summer equinox where the sun hits almost exactly at 90 degrees. And it's very weird because if you take a picture outside, no one's going to have a shadow. Isn't that kind of crazy? Have you ever heard of that? It's this thing where like things don't have shadows. I think it's called Hanalei Noon or Maui Noon. Lahaina Noon. That's what it is. Lahaina Noon, look at these pictures. I can't necessarily say that nothing will have a shadow, but the shadow will be like, look at this picture of the post office. There's shadows in there, I agree, but it's almost like you can't see them. And why is that? Why is Lahaina Noon, why doesn't it have any shadows? Why are there no shadows on this building, or this flagpole doesn't have a shadow? It's because the sun is directly above. It's exactly above, and it only happens twice a year. And it only even happens, there's only places on Maui where this happens. That's why they call it Lahaina Noon. It's the only state in our nation where this actually occurs twice a year, and it happens around May 24th, where the sun is exactly above and you can't see a shadow. The reason why you can't see the shadows is right underneath you. So technically there is shadows, but I mean, whatever. Yeah, it's happened on Oahu, and it's actually pretty cool, and I'd like for you guys to take a look at it one day, because I think it's really cool. But the sun will hit the Earth at the equator or around the equator, or it actually happens in Hawaii, because we're close to almost exactly 90 degrees, because remember, this globe should actually be tilted. But around the equator, it hits the Earth exactly at almost 90 degrees. And that causes the most amount of heating, because it's hitting the thing dead on. We talked about this when we were talking about the seasons. Now, up in the North Pole, it hits with a very small angle. And since it hits with such a small angle over there, the North Pole doesn't get that much heat. And because of that, it gets really cold over there. And that's why it's really cold. It's not because a lot of you, when we were talking about this stuff, a lot of you guys said, oh, it's because the Alaska is further away from the sun. No, that's not it. It's not necessarily that it's further away. It's because it's hitting with a different angle. And when we talked about how it moves, you remember I made you guys take that piece of paper and change the different angles, and you saw how spread out that light got? And then because it got so spread out, that means that the light wasn't like as intense, and so it was much colder in that area. And I hate to say it, but it's 12:30, and I have to finish. I can't finish my lecture. I don't want to stop talking. I don't want to start talking about all of this stuff and then like just ditch you guys. So 12:30. I'll see you guys later. Cliffhanger. I'm sorry, but hey, whatever. I feel like we talked a lot about what we did last year, which is good. All right. Talk to you later. I'm going to end the WebEx.